So roughly the plan is the following. Now the recitation session at the beginning to help you understand a little bit how the basically instrument works. Then we'll go there to take a look at the instrument, so you can see the real instrument. And afterwards, then we'll try to work on some data, pretend that because we do not have Neutron, the data has been taken already, and so we'll give you some data. Then we'll start working on it, and then go through that, and then after that we'll talk together. How do we understand the data? I mean, in principle, and how the community do it. And tomorrow morning, we'll show you a few ways we understand the data we taken from the protein system. And then afterwards, it's more like we basically answer your question, because you need to have a final presentation. You need to start to formulate the ideas. How do you prepare the presentation? Because it's very quick and fast. 15 minutes still, I can provide all the slides you need, but you need to come out the story, right? So I hope that tomorrow morning we can give you an hour-ish to say. So starting for tonight, you can think about what you need the help from us, from Nora, me, and Roshin. Okay? Yeah, just recap our team, the instructor team. Roshin, maybe you can introduce yourself.
Hi, everyone. I'm a fifth-year PhD student based here from the University of Delaware in Dr. Norm Wagner's group, co-advised by Dr. Yun Liu, and I work on protein dynamics with spin echo and SANS to understand the relationship between dynamics and stability for biopharmaceutical application.
Nora, a few words. Introduce to them.
Laura's the best.
Yes, I like that.
Hi, I'm Laura Stinacho. I'm a district scientist at the Spectrometer at Oak Ridge National Installation Schools. It's different. So let's do show you
Thursday.
a little bit about it on Thursday.
Yeah. Okay. Yeah. Thanks. All right. Thanks for. Yeah.
That would mean that you're working on a time-of-flight type of an instrument.
But every spin echo is if you think about it, because it uses the time of flight of the neutrons in the magnetic field. But you are correct in the sense of the time of flight coming from, say,
Yeah, the slide that you showed that.
Okay. Yeah. Thanks, Laura, for coming here to help. Do you have any question after listening to so many things this morning? Any questions? So maybe I'll start with that. Do you think that you have idea how neutron spin echo works now? Or you think that I'm completely lost? I still have no clue.
Partially, yes.
Partially.
I have an idea of how it works, but I don't know how it's interpreted.
Yeah. Okay. There's a separate issues. Okay. And so Antonio talked mostly about what the dynamic means. Basically, really how neutron interact with the samples. So that's how the sample respond to your basically your neutron come in. Michi talking about how the instrument to probe those signals. Okay, so I'm asking that do you understand why neutron spin echo can measure the so-called intermediate scattering function? Okay, this is not test. I just want to try to, like I said, recitation to try to reintroduce some concept already talked this morning, so you have idea. So first, that for any dynamic measurement from our sample, what scatter out of sample is always the Q or delta E. Sometimes we use E, sometimes we use omega, or sometimes people use delta omega. But anyway, this means energy difference. Q is a wave vector difference. So everyone knows what's wave vector difference? The scattering wave vector, Q. Okay. Yeah. Energy difference, that's clear. So this is a so-called dynamic structure factor. When neutron hit that, what the dynamic structure factor essentially is a probability function. When it's scattered, Q is related with U angle. I mean, not a pure angle, but related with U angle. So when a neutron hit your sample at a certain Q and delta E, what's the probability we come out the intensity? That's basically this is about. Okay. Yeah. And Antonio also mentioned the intermediate scattering function. Intermediate scattering function. And I forgot what he used, QT, but sometimes I use FQT. It's just simple different, but it's intermediate scattering function. The relationship with the dynamic structure factor is a Fourier transformation of d omega. So everyone got this? So in fact that for any spectrometer, we already try to measure this because that's what happens to the sample. But the neutron spin echo has a special way to do the automatic Fourier transformation, then they can get the intermediate scattering function. So for neutron spin echo, your signal you get is this. But for what happened to the sample, no matter what spectrometer happens, it's always this. The neutron hit your sample coming out, either it change energy or does not change energy. It's always like this. So no matter use neutron spin echo or use any other spectrometer, that's what come out of your sample, the probability function. It's happened to that the neutron spin echo machine did some magic mathematical manipulation and did a Fourier transformation, get the SFQT, intermediate scattering function. So far we are good.
Yes.
And we'll talk about what's the intermediate scattering function later. But do you know how the neutron spin echo achieve this goal to do this? Okay. Anyone, you think that, feel free to talk a little bit if you think you understand, because then I understand where you are and then I can help you a little bit. Or you feel that, no, I still lost. It's fine, because here you are learning. Because I have to say that neutron spin echo is one of the most, not one of the, I think it's the most complicated instrument for all the neutron instruments. So when I was student at the beginning, it took me a few years to really understood how they, when I say really understood, it's not really, it just understood the basic principles. So if you feel that you're new to this field and you get lost, don't feel frustrated. That's normal, because this is really the most complicated instrument in terms of concept-wise. So maybe I'll try to throw something to you first. Okay, and this morning, and Michi talking about that, they use the phase information in order to encode all the energy information to get this. And that means that neutron need to process in the coil. Okay, procession, okay. So that means that the typical, traditional, or classical neutron spin echo has two magnets, right? And the magnetic field for that is along this direction. So in order to let the neutron has a spin, think about spin a little magnet. So which orientation our spin need to be in order to process when they're flying through the coil?
In the direction. Oh no, perpendicular.
Need to be perpendicular. So that means that for my neutron come in, my spin has to do this way. Okay, then go inside. If my spin this way, they will not do processing. Okay. So now, second part. When the neutron get into the field, this is B, the field, the length is L. What's the frequency? In order to calculate the phase, usually when we think about a phase, we need to know the frequency, right? Now I use same omega, but don't be confused. That's energy. This is the frequency. You need to know the frequency, you need to know the time, and that gives you phase, right? So the frequency for neutron in the magnetic field is basically equal to gyromagnetic ratio. That's a fixed number for different element. That's fixed constant times B. So that means that no matter what a neutron come in, this is fixed, the frequency. So what determines how much is the phase they have from here to here?
Straight the magnetic field.
The time it flies through, right? How much time spent on. But if I know my velocity, if I know velocity is v, how much time they flies through L from here. What-
Distance traveled.
So it's distance. Let's say the magnet 1, the T1 is the L divided by my velocity 1, right? So that's my phase 1. That's my phase 1. Okay. So then when the neutron get into second magnetic field, so someone help me. If the velocity, the field is still B, length is still L, and this is velocity 1, this is velocity 2. What's the phase I can gain in the second field? Someone help me.
So it is gamma B
Gamma B,
L by V2.
bingo. Okay. So for the elastic scattering, what elastic scattering means? No energy change, right? What means that the velocity of neutron will be the same, right? So then V is the same. So that means that V phi 1 and phi 2 is the same, right? So the phase difference here is phi 2 minus phi 1. Okay. If there's no velocity change, then that's 0. So what it means that, okay, then the phase, but how do we compare the phase difference? Then they did some special things. When the neutron passes through the whole thing, and you get the phi, they add a so-called a pi flipper here. It's called a pi flipper. So basically force the phase become minus phi 1. Like that's a pi flipper is about from phi 1 to minus phi 1. So when they go to second phase, then you have phi 2. Then in the end of that, after this, you are looking at the lat phase. So that's what a pi flipper is about. Okay. So that's the principle of this. Okay. So when neutron come here, it's still like this way. Okay. If there's no basically energy change, elastic then. Okay, now how do we probe the neutrons? In order to probe the neutron,
Analyzer.
yes, we need to use analyzer. But analyzer here, we need to, the analyzer direction, they have a coil along this direction. So we need to flip neutron in this direction in order to, so that's why we need to add another pi over 2 flipper. So after the pi over 2 flipper, neutrons here, then neutron coming here, they can go into analyzer. Then after that is detector. Only the certain direction neutron can go through, and this is detector. So, but if you listen to Mitch's talk carefully, I want to say carefully, then if you miss it, that doesn't matter because there's so much information there. So actually, when neutron come from the guides here, the neutron is in, spin is in this direction. In order to go here, what do we need to have? Another pi over flipper, right? Pi over 2 flipper. That's why we add a pi over 2 flipper here. So we have little gadgets here that try to manipulate the orientation. Now I hope you understand why they have this. Okay, yeah. So far, everyone follow. So now the question is that, how do we measure the energy? So if we lost some energy on this side, let's say we gain the energy, what will happen to velocity V2? Will become, because the energy increase, the V will increase, right? Velocity will become bigger. So that means that time flies will be smaller. Then phi 2 will become smaller, right? So then delta phi will be bigger. Okay. So that means that the energy difference, which is related to the frequency, related to the difference of the phi now. Okay. The coding in the phase information. Okay, so Yeah, I have little cheat sheet to help me to remember all the details. Yeah. So
But you said like, so V2 is increasing, right?
yeah, if
So
they
Q2 will
gain the
be-
energy.
Q2 will be smaller. I'm sorry, phi2 will be smaller. And
Yeah.
so the delta Q should reduce, right?
Delta phi, they should, the
Delta
phi 2 will be smaller, but delta phi will be positive now.
Okay, yeah, because
oh, sorry,
yeah.
negative. Yeah, I
Yeah.
got that. Depends on how you write this. Okay. Thank you. You corrected me. No, you're right. Okay. So then the delta phi difference here basically is become gamma B L 1 over V1 minus 1 over V2. These are relative instrument only, and this related with your basically the property of the wavelength of a neutron. And if you go through that, I'm not going to go through the details. And roughly this equal to gamma B L m square divided by 2 pi and 1 over h square and lambda 3 times delta omega. That's this delta omega. So that's the relationship between the energy difference and the, okay, this we called Fourier time of this neutron spin echo, or correlation time. Sometimes I use the correlation time, sometimes people use the Fourier time, TF. Okay. So far, everyone get it? So the key is the physical principle that is when the flying time is different between the two magnetic field, that causes the phase shift. And Michi showed you the is many wrong turn of the phase goes through. So this is extremely sensitive to any small energy difference because they all come to the phase change information. Okay? So now the following is a bit of a straightforward. So remember that when neutron come in, the probability scatter the how much energy change is SQ. Maybe I use delta omega. That's a probability we change. So when we do the polarization analysis, the polarization analysis is very interesting. The polarization analysis is that is for every neutron here, and the polarization analysis is cosine delta phi. Yeah, that's related with that.
Just one question.
Yeah,
This
go ahead.
M is mass of the particle. What is
That's the M is a neutron mass.
a neutron mass?
Neutron mass, yeah, because neutron do not fly that fast. It's the Antonio tried to use the millimeter per second. I try to use the kilometers per second. So usually it's like a couple of kilometers per second. I think the kilometer per second. Basically, it's about the bullets, the flight of bullets. That's how fast the neutron flies. It's not very fast. If the instrument built far enough, you can see the gravity effect. Neutron will drop on your detector. Yeah. So that's a different story. So, okay, let's focus on only this cosine term. That's due to the property of the polarization. The details you don't need to worry about. And that's cosine delta phi. Okay. So that leads to Fourier time times delta omega. Okay. But keep in mind that when the neutron come out of the sample, they have all the energy change. There could be small energy and big energy change. You need to integrate all the energy change. Look at this and compare to this. If I change here to delta omega, because this term usually is a symmetric function as energy, so this is equal to the same thing cosine delta of omega t, d delta of omega. They're identical. Look at this. They're identical, right? Everyone follow me? They're identical from here. So essentially that's this one. This means that this is equal to the Fourier time. So the couple magic here, first that we use the neutron spin angle, the instrument, depending on flying time, we encode the energy difference into the phase information. That's the first step. Second step that we use the polarization analysis to get the cosine term built inside, and then intrinsically it did the Fourier transformation for you because we collect all the energy from the instrument. Okay, from that scatter from sample. Then essentially that give you intermediate scattering function. Okay. So now we're talking about this Fourier time is very important. That's related to samples fluctuation, how long the time correlation we're talking about. It's nanoseconds, picoseconds, or microseconds. And so what controls the Fourier time is from here. Now you can see that what is controllable. This one, can you do it? Gyromagnetic ratio. Unless you change the neutron, that time you cannot change it, right? Can you do this one? L. The magnet. Oh, you can make bigger magnet, right? Longer magnet. Well, and or you can make B larger. So B times L. That's what Antonio talking about, integral field. So you by increase B, but then you see that if you increase the magnetic field by factor 2, how long the Fourier time will change? Factor of 2, right? 2. Yeah, factor 2, because that's a linear relationship. Okay. The neutron mass, I guess we cannot change it unless you have some magic, right? 2 pi? Okay, that's constant. And if that change, our universe is changed. Okay. And that's Planck constant. Nothing we can do. What else we can do? Wavelength, right? And the magic part of wavelength to which part? Third part. That means that if you double the wavelength, how long the Fourier time you can change? Factor of 8. Or almost all the magnitude. That means that if you want to go to longer Fourier time for neutron spin angle environment, the best way is what? Non-wavelength. But the problem, there's just one problem. Usually for neutron, the flux is going this way. As a function wavelength and the flux of neutron. Usually on this side. I mean, longer wavelengths, you have much smaller flux. Okay, so it's a balance of these two, where is the best, optimized situation. You need to think very carefully. But in principle, that you can increase the magnetic field. So right now, the neutron spin angle is undergo an upgrade, and one way they do, they try to use the superconducting magnet coil, and so that we can increase the magnetic field, I think by factor 2. Yeah. So then you can see that. But that means that even use a factor 2, what you could do that is you can use a different wavelength, a shorter wavelength, which is same. Because when this increase, you can keep the Fourier time same, but you can use a different wavelength now. But which means that you can move to shorter wavelengths. You can have more flux. Okay. So
It's on the y-axis of that one again.
it's the number of the neutrons.
Okay.
In terms of that's the neutron flux and how the distribution looks like. This is a question.
Are there some materials that you don't need a lot of flux to get a good signal?
Yeah. I mean,
I'm just trying to.
Yeah.
Some examples?
yeah. So, I mean, now you need to determine that based on basically you can measure with your Smangle neutron scattering.
The ones that scatter strongly.
Then scattering strongly, then you don't need to worry about. Then you can easily go to longer wavelengths. Will be fine. Okay. But also keep in mind that Antonio mentioned this morning also, usually the low Q, you need a longer wavelength. Then you have a slower relaxation. That means you need to measure longer Fourier time. So anyway, that means you at low Q, you tend to use longer wavelengths to do your experiments. And the high Q, usually your relaxation time anyway is very fast. You don't need a very long Fourier time. And in this case, you can use shorter wavelengths to do it. Okay. So this one, important part is just proportional to the field integral is a linear relationship with the wavelength, the lambda cube. Keep that in mind. If you can remember that, bingo, that's good enough. I hope that helps you understand a little bit better how neutron spin echo works. Okay. Do you know when is the coffee break for you guys? 3:30, I believe, right? Yeah. Yeah. So any questions so far? And if I erase all of this, and some of you can tell me and can teach other people in a simplified version how neutron spin echo works, right? Well, I'll ask Roshan maybe later you can help me make a copy to you guys if you need this. And you don't need to worry too much about it because I read here. Any other questions? No? Yes? Okay. So now, question time. Hope quick. I'm not going to grade it. Why we need the pi flipper? Someone can tell me.
That one
To get
specifically.
The pi flipper, right? Yeah, we need to change the phase, flip the phase from, yeah, so that we can directly measure the phase difference between two. So why we need is the power 2 flipper here?
Because what comes out is now actually parallel to analyzer. We don't want that. Sorry, what comes out is perpendicular to the analyzer, but it has to be parallel to the analyzer for the analyzer to actually,
Perfect. Why do we need this power 2 flipper?
because the
it has to
neutrons
be
come
coming
parallel,
in.
but we need to fix that.
You guys pass 100 points. Full score. Yeah. So I think if you get this idea and keep in mind that the relationship for dynamic structure factor, this is dynamic structure factor, with the intermediate scattering function, the Fourier transformation, then keep that in mind, you are good. And for the user point of view, and that's I think what you need in order to know how to use neutron spin echo from the principal side. Unless Laura has a different opinion, say, okay, you guys need to understand much more. Okay.
Actually,
Yes, go ahead.
I did not understand clearly in the previous talk is also what he talked about 2 by thirds and 1 by thirds contribution to the incoherent.
So it's
That's different. That's different one. That's different story.
Comes later.
Yeah, it will come later.
Start acquiring data.
Yeah.
Okay.
Because okay, it's related the following is what signal coming through. Because here that when we interact the sample, we assume that the phase coming out they keep the same phase. Because remember I said the phase flipped and going to the third one, going to the second one, that's phase. That means that when neutron interact the sample, their phase will not be changed here. That's not always the case. For incoherent scattering, they will change. But 1/3 of them keep the phase. 2/3 of them you just lost it. Okay, so then that's what 1/3. But the good news that for what we are interested in right now here is a coherent scattering. For coherent scattering, the phase always keep there and they do not change that. Okay, so you don't need to worry about that part. But that's a very good question. Any other questions? So I'm here to help you. So I'm your TA. Okay, tell me what you don't understand, then I can explain to you.
So the only reason you have a pi flipper in the center is because you couldn't have your second magnet be the opposite direction because then you
That's
have the
correct.
zero zone.
Yeah. Well, I mean, in old time when I was trying to teach neutron spin echo, I try to tell people I flip the magnetic field for the second one, but in reality that's harder. So then we put a pi flipper there. Okay, yeah, that's a very good question. Yeah. Any other questions? So you guys get.
So if the pi flipper is missing, what happens?
Nothing. It didn't get flipped. So it just goes straight on through.
Like an echo or like
Yeah, if I understand correctly.
I don't. You wouldn't get an echo because the
Okay. So I didn't talk about the echo part yet,
Okay.
because I only talk about what's the relationship. So why? Okay, now can you erase this now? Okay.
Yes.
So I'll erase this. I think that this is okay. I'll erase here. So we're talking about the two magnet is completely identical. The reality is that they're still different. Okay, there will be a little bit of difference. The difference comes from somewhere. Okay, the difference comes from, okay, here. Okay, so we're talking about the phase difference. If they are the actual phase, that is to say, the magnet B are a little bit different, but in reality, flying past many things can contribute. So your reality is that what you get is SQ delta omega. When you have a cosine delta phi due to the perfect one, you have an actual phase. That's I call the shift phase due to whatever reason. That's imperfection, right? And then I have d delta omega. So without going into details, okay, I throw away sign term, integrate all the energy. It's the same thing and cosine phi s d delta omega. And this is related to just your phase shift for a certain point. So then this is a constant term. So you end up SQ tau f cosine phi s. That's just your phase shift. So that means that, but what we are interested in is this one. Sorry, TF. What we are interested in this one. So we need to find out the amplitude of this cosine term. So what do we do? So what do we do actually? We have called a phase coil for this term. So we artificially introduce different phase, and then what you get is that as a I didn't plan that, and so they put the field. What did they?
The phase.
Yeah, the phase. Yeah, okay. They call the phase here.
Phase current.
Yeah. Oh, that's related to current. Yes. Thank you. And so then they measure a few data points because it's a cosine term, right? So they should have a cosine function, follow a cosine function. And by fitting that, I can get my amplitude term. That's what I mean. So when the phi s is 0, that's your perfect echo. Okay. Yeah. So this amplitude for this one. So which means that for fixed Fourier time, in order to get this amplitude term, we need to measure many points. Okay. This varies from instrument to instrument. At the NCR, I believe that they measure 18 or 19 phase points in order to get the amplitude. Okay. Yeah. So that's one reason this is take time, because in order to get a one Fourier time, I have to measure 19 points. Actually, not only 19 points. There's more for up and down, but we'll get to that point later. Okay. So, but the phase part, do you know why it comes? Because I mentioned that, but so because when you build two magnets, they will not be completely identical. It's impossible. Plus, when neutron come here, they scatter. They will come in this way. The path will be slightly different. So that means that at a different angle, sometimes their phase shift will be a little bit different because the coil, because the flying path is a little bit different. So when you do the experiment to data reduction, and well, if you come to NCR, Antonio and Mitch will show you how to data reduction. One important part is to understand how to find the phase information, and by fitting this, get the phase shift information import to that, so that you can correct and analyze data. I'll briefly show you how it looks like. You don't need to go through that. Okay. In the end of that, usually when you finish that, you should get the intermediate scattering function. That's what you need to worry about. Okay. This is related to how we do the data reductions.
One question.
Yes.
So the number of points here.
Yeah.
In the experiment, is it related to a counting time?
No, this usually is fixed points. Fixed point.
But
In order,
they do have a counting time.
yeah, they do have counting time.
Count for a particular time.
Yeah.
Yeah.
Enough statistics. Yeah. So basically, it's 19 times whatever actual point times total counting time you have. That's how much time you need in order to measure one Fourier time.
If you have only 3 neutrons contributing to that particular, so think of them Sorry.
Yes, okay, go, please.
So, the whole purpose of this echo is so the phase shift. Think of it like this. I have relaxation due to the interaction with the sample, but also due to field inhomogeneities between the two magnets. That one I can control to a minimum, 10 to 5, 10 to minus 5, 10 to minus 6 ppm, but no more than that, right? So, because I have no control in that, if I leave this to nature, this will accumulate in the end. But I cannot measure, I cannot detect the influence of that on my polarization. I need to control how much polarization I have, how much polarization I lose, how much polarization I'm getting in the end. By polarization, I mean, like in NMR, the magnetization, the signal that actually passes through, right? So what I do then, this is how I explain it to my student. I try to keep these two as identical as possible. And then I come with a phase coil. And with the phase coil, I induce a loss of polarization. I create a discrepancy between the first and the second coil. I induce a non-homogeneity in the field. Because why? Because it's easier to control. Because I induce, by that I mean this is just a small coil, I put current in it, right? But I have disturbed the whole field in this magnet, right? But that's an inhomogeneity that I can control, right? And then based on comparing that with that, I get my loss of, so your echo is not just a random accumulation of points of something like that. So when the echo that looks like that, each point that he's talking about, each phase point, phase 1 to phase 19, corresponds to one polarization signal that I actually get in my detector, right? So I keep this constant. Here, there's the phase coil inside. I put one current in the phase coil, my polarization like this, and I end up with a little bit of polarization, right? I start with P, and I end up with P1 due to Phi1. That P1 is this one here, right? Because I do not know where my maximum polarization that I can get, where my maximum amplitude is. I have no idea where it sits in this phase field, right? So then I have to scan it. I put another current here, I get a P2 here. And then this is the P2, and the P3, and so on, and so far, P19, and then I feed the cosine function to this one. So basically, I get the center of phase, and I know at this phase current, I get this maximum amplitude. And that's the value that I finally use. I will say, this echo has this amplitude, and this amplitude will go farther in the calculation of IFQ and tau, right? So it's all based on this phase inhomogeneity, but I induce it because I can control it. It's easier to control. This is how I explain it. Sorry.
No, thank you. You're welcome. Everyone has a different way to explain the same thing.
Sure.
That together will help a lot. Any other questions? If no more questions, I think that we'll take the time before the coffee break to go to see the instrument. Then you can see how the power 2 flipper looks like, pi flipper looks like, how the magnet looks like. There's a phase coil. Remember, there's a big coil, main coil inside. The phase coil, just a small adjustment of the phase inside. Any questions before we go to the guide hall?
So this is performed irrespective of what samples you use. This you perform to understand the instruments.
It's the same.
It's the same measurement for all the samples.
This is the technique. This is how it works.
Okay.
Yeah, this is how we measure.
No matter polymer, protein, whatever magnet, whatever you put in the middle as a sample.
Yeah.
Okay.
This is.
I'll show you example later.
Yeah.
Okay. Good questions. Questions? I mean, so I know that the people's background are quite different. There are people have some neutron scattering experience, and some people have no neutron scattering experience. Just like Bela yesterday said, no stupid questions. Feel free to ask any questions. Yeah.
And also just try to grasp the concept.
Yeah.
Because there are hundreds of books out there full of equations and of, but ultimately evaluations of the basics of neutron scattering. Ultimately, as a scientist or future professors, those are not very important for you unless you want to become a neutron scattering scientist
Yes.
yourself,
Yeah.
right? You just have to grasp the concept so that you understand how to apply it to your science.
Yeah.
Because ultimately, this is what you want. You know,
Yeah.
it's not going to help your PhD if you're able to derive all the scattering information, because
Yeah.
that might not be your thesis,
Yeah.
right?
So that's why I say exact formula here doesn't matter.
Doesn't
Just keep in mind that
Yeah.
the lambda dependence, because that
You can
determines
find
we.
it in any textbook or.
Yeah. It's written there anyway. You can find it anywhere. Okay. All the phase, if they have a no, let's say if they have no basically the neutron, and then everything come back the same place. Okay. Yeah. So, but if you have some phase that is not right, then they may go to different directions. And so when you do the polarization, because we do not say this one, when you do polarization analysis, only say this one. Okay. So the echo basically means that that's what you get. You are saying when you have different phase, then that's what I mean cosine term. You have this, right? And so basically that your phase, if your phase perfect line with everything, then you have a maximum. Absolutely, that's where you get all the echoes. That's how I call the echo. But Nora, you are the instrument scientist. Maybe that's you guys have different one. I call this is echo points, and but you can have many other things. But how? Okay, in reality though, that you're not all the energy is the same, and so then if not all the energy is same, then you have loss. So that means that's what Nietzsche said. Even you have perfect echo points, but there are some neutron gain, some neutron loss. But overall, you have a distribution of this. But overall, the average direction is still this direction. That's still echo point. But if you introduce phase, the overall the phase may shift to this direction, but the average go to here, and this is not the echo point anymore. And the echo point just that's perfectly lined up. That means no phase shift on the both sides. That's how I interpret that. Or, yeah.
So I guess your confusion is why the hell is it called an echo?
Yeah, exactly. The term itself.
So it comes the name itself. We are so proud when Medsey come up with this technique, but it's actually a very old technique, the same spin echo from NMR. It actually has been developed, the concept of spin echo has been developed by a guy named Han, and it is called Han echo in NMR. It is the spin echo and Han echo are the exact same thing, right? So what is it actually? It is this ability to manipulate and refocus the polarization by applying a series of RF pulses, right? So what do? You come with a 90-degree pulse, right? And they start to precess, right? And at any point in that precession, it doesn't matter where, right? They will accumulate a phase shift. You come with 180-degree pulse. It's called a 90-degree pulse, which is your pi half flipper. So pi half flipper is just a coil that gives you a magnetic field orientation at pi half 90 degrees, right? Pi flipper, it's a coil that you put current in it and it gives you a magnetic, it will flip your neutrons, magnetic field orientation 180 degrees. 180 degree, it will mirror. So you apply the 90-degree pulse, they start to precess, they accumulate a phase, right? At any point in that phase accumulation, you come with 180 degree. Think of it, Mishi showed you the fan, but he actually didn't show it the way I show it to my students. You can do it even with your hands, right? These are my neutrons. I apply 90 degrees, they go like this, right? This is the main superconducting magnetic coil. They start to precess, right? So they accumulate a phase shift, right? Which means that they start to deviate like this, right? And they go to, but they actually rotate, right? But let's assume they go like this, right? Okay, so they dephase and they keep dephasing. if I let that 90, after that pi half flip or that 90-degree pulse, if I don't do anything, they will dephase until I lose my entire polarization. There will be no signal. So what I do at the sample position, it doesn't matter where, before or after the sample, you come with an RF pulse, or you have a coil, you set a 180-degree pulse in it. That means 100-degree means that it flips your orientation it mirrors 180 degrees, exactly like you're looking in a mirror. So my spins, they're doing this and they're moving forward. I come with the 180 degree and I turn them like this. They're stupid. They think they're still going right, because I have this one that was going this way and this one is going this way, right? But now I kind of flip them 180 degree. This one goes, he thinks he's going this way, but he's going this way. This one is thinking he's going that way, but I tricked them. I just mirrored them, and it's going this way. So they were doing this. I flipped them. They are now doing this. So if your B and B are equal, and the sample that doesn't change the velocity, they will spend the same amount of time in the first magnet and the same amount of time in the second magnet. So everything that they dephase here, when I trick them and they do this, they will accumulate back, and there's my polarization. I come with another, because my polarization is like this, I come with another 90 degree, I put it like this, that's my whole polarization in the detector. If your sample doesn't scatter or it's a perfect elastic scatter, right? So echo, it comes that it's a mirror, but we cannot say a mirror, it's an echo of my polarization.
Oh God. Okay.
So basically in the
But it's hand echo. So on Wikipedia, just go and look at hand echo. It's the same. Hand echo and spin echo are the same thing. It has not been invented for neutron scattering. It has been developed for NMR first.
that's correct.
And we just took it from that. That's right. And this is what I say. It's echo because they cannot call it a mirror of the polarization. It doesn't sound that well. It's an echo. But it's basically.
But echo means that you have maximum point at that particular time. You do, if you do an NMR, look at the time scale for the T2 relaxation, you flip it. At the different places, the magnetic field may not be very uniform. Local magnetic field may not be uniform. Even the same spin, then they may not process in the same time. And so then there was, like Michi said, the fan out, the distribution from here to here.
Yeah.
But if I flip that in other direction, I cannot do it myself.
Yeah.
And go this direction. But they go the same after the same time. They all come back the same place. Because at the beginning, if this one goes faster, I flip that, they will still go faster. They go back after the same time, go back same place. If I go slower, I flip it, I go slower. So all the spin, no matter they go fast or slow, due to the local inhomogeneity of magnetic field, they all come back exact same location. Yeah.
That's
So
the 90 degree before.
what?
Oh, yeah, the flip.
Yeah, flip. That's what we're trying to do.
Just to keep it at 90 degree.
No,
we still same. We just 180
You do
degree.
the 180.
yeah,
but
that's to
you-
mirror them.
Yeah.
Right. And
If you don't mirror them,
then they're
they
gonna
will
keep you
continue to
Yeah.
keep dephase, and
Yeah.
eventually you will lose
You
everything.
lose everything.
Right.
You will not
lose
have
it.
the.
You will
You will
not
not have
have
as echo. Yes.
You will not have an echo.
Yeah. Basically, that's why we say we need to look at the phase difference of the two, right? Yeah. Yeah. Okay. Actually, we're getting the coffee time now. We should come back later.
Well,
Okay.
it's better if they understand. But let's go. I mean,
So is your echo a max, like the maxima that you get from?
Yeah.
Yeah, it's a
from-
maximum intensity you have. Yeah.
so you're searching for that maximum amplitude.
Yeah.
The echo
By
is
doing
the
the- by the-
entire
yeah.
envelope that goes.
By doing this cosine function, look
Echo-
at the amplitude, and
So
that's
what's the-
characterized
yeah,
by
correct.
the amplitude and the phase current descent.
any
The echo
questions?
is the whole envelope.
Good question. Good question.
There's a lot of questions, but I think it's good enough.
Okay. So you feel your brain is burned already, right?